So let us now take a brief moment to summarize what we have done so far. So we have defined this distance function, and we've seen what are the key properties of the distance function. And so a distance function is a function that is defined in general on any set that would assign to any pair of two elements their distance, right? And we have seen that this distance function better satisfy three crucial properties. So the first property that we want any distance function to satisfy is this positivity, that it's non-negative and it is zero if and only if those two elements are the same. We want this to be a symmetric function, and we want it to satisfy this triangle inequality so that all our intuition about, say, Euclidean geometry and about distances is being preserved. And so then everything that we said can be vastly generalized to abstract spaces, and I think it's very, very important to introduce this more abstract way of thinking in parallel with the basic concepts, so that this intuition and the way that it generalizes to more complicated spaces comes together. So if I were to quote David Hilbert, so he said that mathematics is the art of locating those special cases that contain all the germs of generality. And so this is what we're doing here. We have noticed that to define this limit or closeness, we need this way of measuring distances. And if we measure distances, then there is some function that measures this distance, and it better satisfy those properties. I mean, those properties are desirable. Okay, and so then when we have this ordered pair of a set on which a distance function has been specified, this set is called a metric space. So what we have showed so far is that the real line or the real numbers together with this distance function, where dxy is the distance between x and y, right, is a metric space. That's what we have proved. And if we define this function, then this function satisfies all those three properties, and therefore this function is a metric. And so with this terminology, R in D is a metric space, and it will have many of the things that we will prove for this space are naturally generalizable to abstract spaces, right? So if we'll define the notion of convergence of a sequence with respect to this distance function, then it naturally generalizes to more abstract cases. Okay, so now let us get back to the definition of convergence and limit. So we have seen so far then when we take this sequence, the sequence that we have seen that this limit, at least intuitively, we expect it to be 0.6. And so we have also seen that the distance between the limit and the elements of the sequence can be made as small as we please, provided that we go far enough. But what is this notion of far enough, right? So for example, it is not enough to say that infinitely many elements will be as close to the limit as we please, because for example, this sequence an, which is -1 to the power of n, if we think of it intuitively, then the sequence oscillates between 1 and -1, so this sequence tends nowhere, and so we'd better have a definition that says that according to this definition, the sequence does not converge, right? But if we look at the value 1, for example, then for infinitely many elements of the sequence, their distance from 1 is 0, and there are other infinitely many elements, and their distance from -1 is 0. So it's not enough to say that infinitely many elements are as close to the limit as we please. We need to have that all elements, probably except for finitely many, will be as close as we please. That's the way to proceed, and we'll see how to do it rigorously. And that's the point. So as we've seen for the previous sequence, we've seen that starting from some point, right, from some very big natural number, from this point on, for example, for the sequence 1 over n, for every n that is greater than 1000, then the distance of the elements of the sequence from the limit is less than 1000. So Now we verbally define what it means for a number to be a sequence. And so the distance between an and l should be, we should be able to make it arbitrarily small when the index of the element an is big enough. So the question, how big is big enough? So now when we want to make this notion of distance precise, we use this distance function, right? But in any metric space, as we would see, whenever we have the notion of distance, we can also have the notion of, or define the notion of convergence, because we measure the distances here. So this distance between elements of the sequence and the limit can be made as small as we please for n that is big enough. But how big should n be, and how big is big enough? Well, it depends how small we want this expression to be. The smaller we want it to be, the bigger this n needs to be. Okay? And so the idea, and what does this mean to make arbitrary small? So as we've said, if I want, I can make this difference be smaller than 1000. And if I want, I can make it smaller than 1 billionth. And if I want, I can make it smaller than 1 billionth of a billionth. So we were to say that for every positive number, as small as it may be, from some point on, the distance of all the elements from the limit will be smaller than this epsilon that I choose. And I can choose epsilon to be as small as I please, right? So now it remains to see how big should this n be. So of course, in general, it would depend, unless our sequence is constant, but if a sequence is convergent, that we would expect that the smaller we want the elements, the closer that we want the elements to be to the limit, the farther we need to go. And so the smaller I wish this distance to be, the farther I need to go in general with the elements of the sequence. So how far I need to go depends on epsilon. So there exists some natural number n, which I will call n of epsilon, because it depends on epsilon, right? And then for every n that is greater than this n of epsilon, this distance will be smaller than epsilon. This is a difficult part to understand, but we will see a visualization of this. But this is basically the definition. So let me restate this once again. So the distance between the elements of the sequence and the limit can be made arbitrarily small, provided that this index is big enough. So starting from some point, from some natural number n that may depend on epsilon, all the elements with index bigger than this n of epsilon, their distance from the limit will be smaller than epsilon. So let us now see this visualization of what it means.